Hello, everyone. My name is Paolo Fittipaldi, and I am a second-year PhD student at Leipzig in Sorbonne University in the QI team, under the supervision of Anastasios Giovannidis and Frédéric Grosson. And today I'm here to tell you about our latest work, a linear algebraic framework for quantum internet dynamic scheduling. So before we delve into our work, I've thought that it's better if everyone speaks the same language. So I will very, very quickly go over some elementary concepts that we need to understand what the setting of the problem is and what it is we are trying to do with this work. So first of all, our motivation is extremely straightforward. If you look at quantum networks, I don't know how many people have had experience with quantum networks in this room, but in quantum networks, the setting that we have right now is that the hardware is not quite ready yet. We have quantum networks in their infancy, like 3 or 4 users on a tabletop. But there is starting interest towards protocol design and towards how to develop these networks, because when the hardware will be ready, we want to be there with all the protocols and the architectures to be ready to build actual world-scale networks, such as the quantum internet. So the key point here to understand is that in quantum networks, we are facing right now, and we will face in the immediate future, the same problems that classical networks already have solved. So the idea here would be to try and use that know-how, all that base of knowledge that we already have, to see what can be carried over, what needs to be adapted, and what needs to be redone entirely. Because, for example, I could tell you that as of now, the best possible quantum memories that we have a retention of about 1 millisecond. That means that you got to work around new limitations, new kinds of impediments that you didn't have working with classical networks, while on the other hand, you need to solve problems such as routing, such as scheduling, such as all the problems that people have had to solve in the past to build the classical internet. So a really extremely bare bones primer about what we are going to talk about, just so that we're on the same page. So in quantum networks, the important thing that we are working with is quantum entanglement, which is a peculiar property of some quantum systems that is extremely useful in terms of applications and in terms of things that you can realize with quantum technology. So starting from the quantum physics 101, when you have a quantum system that can be in a number of states. So let's say, for example, the spin of an electron, it could be up or it could be down, let's say. But actually, quantum systems, when you leave them exist, when you leave them unperturbed, will not be in a definite state. They will be in what we call a superposition of those states, so that at any given time, the state of our system will not be completely determined. To determine the state of the system, you have to make a measurement. And when you make a measurement, you actually collapse your system in one or the other state. And this is extremely important. It's not like we cannot know the state of the system. It's really that the state of the system is not defined until we observe it. This, I'm gonna need you to trust me on this one, but this is the core concept that we are gonna work with, because quantum entanglement is the property that can be shared by 2 or more parties, such that whenever we have 2 or more parties that are entangled and we measure one of those parties, we actually collapse all of them. And this is invaluable in terms of application and in terms of what we can realize with it. So that what we stress here is that the main purpose of a quantum system would be to be able to distribute entanglement to 2 arbitrary parties. The problem here is that quantum entanglement has some technological issues. in that it must be distributed with extremely weak signals, often on the level of the single photon. So it has to overcome extreme losses. And also it is a process that is inherently probabilistic. So if we set all the factors together, what we obtain is that the probability to be able to distribute entanglement to two parties that we have scales exponentially with distance. And this is, of course, extremely bad. What we can do to counter this is to exploit the protocol of entanglement swapping, the technique, better, of entanglement swapping. So what we do is we distribute entanglement to some elementary nodes, like A to B and B to C. We place those nodes close enough that we can reliably distribute entanglement to them. And then we store that entanglement in some quantum memories. What we obtain is that, for example, we have success along A and B, but B and C is not quite ready yet. So we store the entanglement in A and B, and we wait for B and C to be ready. And as soon as we have elementary entanglement along A and B, B and C, there is a particular measurement that we can carry out on the photons or electrons, on whatever system it is you use to implement your qubits. You can carry out that measurement locally at B, and what you obtain is that you project A and C into an entangled state, so that you can effectively extend the distance over which you can distribute entanglement, in principle, arbitrarily. Actually, what you obtain, if you go and work out all the calculations, is that you observe a polynomial scaling versus distance instead of an exponential one. Yes.
Just a comment about what you said. You didn't tell that, but it is important for people. There is no faster than the speed of light transmission of the entanglement.
Yes.
When you do the measurement in B, you need to send the result
yes.
to C or to A to transmit the entanglement.
Yes, exactly. This is, yeah, actually, yeah, this is.
Actually, I know that you know that, but you didn't.
no, just to rephrase it for yes. This is actually a fundamental clarification here, is that yes, if you measure A, you instantly affect C. That is true. But since there's no free lunch, you're not violating special relativity here, because actually you do affect C, but to carry out any meaningful application, you still need A to communicate the result of their measurement to C, so that some processing can be taken on C's part. The peculiar thing here is that, of course, if I say it like this, it will seem like, yeah, okay, so the actual communication is only between A and C, so there is nothing new here. The peculiar thing here is that when you perform a measurement on an entangled system, first of all, it needs to be stressed that A and C, once you have carried out the distribution, can be arbitrarily far. They don't need to be connected in any way. This is a property that doesn't depend on distance. It's a non-local property. And also we need this transfer of information because, as we said before, we measure the system and we collapse into one of two states, but we cannot know a priori which one. So we need this transfer of information because C does not know what they have there, because we collapsed our system, but at C, no measure took place. So the qubit that there is at C is still, C cannot know what value they have. When we give the result of our measurement from A to C, the people at the node C can perform some post-processing on their information in order to carry out our protocol. Yes?
Quick question. You said errors become polynomial when you do entanglement swapping. Does that suppose that entanglement swapping always succeeds? Or is that also, does that also hold if you have a probability of error?
No, it does hold if there is a probability of error. It's more a matter, it's an effect that you obtain when you introduce memory at the slot, because actually the first step that you do is you introduce the nodes that can perform swapping in the middle, but they're memoryless. So you still wait for everyone to have success, and so the scaling is still exponential. When you introduce memory, you can afford to wait some steps, and so the scaling becomes easier. It's not exponential anymore. So going back to the core informations we need to understand our work, entanglement swapping allows us to extend the distance over which we can distribute entanglement. And it is, of course, an operation that can be iterated. So that if we have, for example, 5 nodes in a row, we can perform first swapping operations at 2 and 4 to obtain this configuration, and then perform one final operation at 3 to have entanglement over our full chain. And our goal, yes?
You talk about distance. An idea of distance, is it, I mean, from 1 to 2, it's 1 kilometer or 1,000 kilometers, 1
Usually,
centimeter?
no. The kinds of distance that we use range from the 50 kilometers to 100 kilometers. You can push it to 300-400, but you have to remember that, just as I said before, the elementary distribution scales exponentially on distance. So the further apart you have the nodes, the harder it will be to have elementary level entanglement. But of course, your network will be bigger because you can push the nodes farther apart.
Just to give an order of magnitude for the losses, 50 kilometers of fiber is a factor. You divide by 10 the number of photons you will see each 50 kilometers.
And often the protocol, now it's in terms of blue circles and dashed lines. So, but what you actually will have could be, for example, 2 nonlinear crystals that produce pairs of photons. At each node, one you store and one you send over a fiber channel. And then at a station in the middle of the node, you interfere them and then you measure so that you erase the information on where the photons came from. So what you obtain, for example, in this case, could be that only one of the 2 nonlinear crystals has generated a pair of photons. They have stored it. They have sent their photon over the middle link. At the base station, you cannot know which one sent you the photon. But so actually, you project the 2 memories that you have at the side nodes in an entangled state. Or you could have, for example, that you generate straight away an entangled pair here, and you send one of the 2 photons over the fiber. But at the end of the day, the point here is that we need to send single photons over very long distances. And that's something that creates a bit of problems. So yeah, entanglement distribution, entanglement swapping.
Sorry?
Yes.
The factor you mentioned, Ludovic, is related. I guess it's related to the interaction of the photons with the matter. But is there do you think it would be possible to design future matters that will reduce this factor?
Today, the optimal way to transmit photons at long distance with good control are fibers, which are very with the fibers having very low losses. But losses, if you take 15 kilometers of fiber, you lost half of the photons. But because it is exponential, then
no, I understand. The fiber has to yeah.
I was going to add that some recent studies have done it through vacuum with satellites, and that works better. But you have to be able to send it straightforward in a vacuum with long distances. So that's one of the improvements that we see in terms of matter, where you're actually directing the photon. You know better.
I think if the optical networks exist for a long time now. I worked on optical networks 25 years ago, and it was already existing, and we didn't find something better than fibers to transmit light on Earth. We didn't find something better than that. It's better in space because there is no loss in the vacuum. But to my opinion, to my knowledge, there is nothing better than glass. Fiber is just glass, which is very pure. there is no better way to transmit photons on Earth, to my knowledge. So maybe there may be other material, but I don't know a better material, and this is something that if it would exist, it would be interesting for optical networks that exist today. Sorry for the interruption.
No, don't worry. It's really interesting. So, okay. Entanglement distribution, entanglement swapping. So we can, in principle, get entanglement over arbitrary lengths. The next step is to take a lot of those chains that you see there and intersect them in some arbitrary way. This would be what we call a quantum network in the future. So our spheres here would be quantum switches, which are devices that are able to perform entanglement swapping operations. And these dashed links that you see here could be fibers or could be any other way that you find to transfer light between the two nodes. So now that we have some elementary information, we can understand what the problem we're trying to solve here is. So first of all, a quick description of what the problem scheduling is in classical networks, because what we are trying to do closely mirrors what people have had to do before us. So suppose we have a classical network, so that our circles are nodes in the classical sense, and all those dashed links are links between our users. Suppose, for example, that this user wants to send a message to this user over there. What you will have to do in the first place is to find a path between those two, which could very well be this one, let's say. This is the problem of routing, which is very well known. But what if some other pair of users wants to communicate? Let's say, for example, that this user wants to communicate with this other one up here. We have our path, and as you see, they cross in the middle. The problem of scheduling arises when we need to send packets along those two routes, and we get to this node where the routes cross. We have to decide who gets to pass first. We have sort of to put traffic light at that intersection. And solving this problem, of course, in much bigger scales and for all the nodes, would amount to what we call the scheduling problem, and would give us a scheduling policy. A scheduling policy is essentially a set of rules that allows us to say, whenever we have such conflicts, to understand who passes first and how we decide who gets to pass first, who gets to pass second, and how the users in general get to use our resource. This, as I mentioned, is an extremely well-known problem, and such as this reference work, which is extremely well known in classical networks, and proposed the max weight scheduling policy, which is one of the first examples of properly fleshed out scheduling policy, which is still studied today in actual network problems, even if it's not actually used in network systems. If we now shift to quantum networks, we can phrase our scheduling problem, but we need to adapt it a bit, because as I've mentioned before, the task of a quantum network is to distribute entangled pairs. And if you think about it a bit, you will realize that the distribution of an entangled pair is not a directional process. I don't have a message that from here starts and goes here and then it goes here. Rather, I have a distribution of a pair across here and then a distribution of a pair across here, and I can grow it through a swapping operation to be a longer one here. And this is essentially the core difference that we have conceptually in the description of the problem, because the problem that we will have now will be, for example, that this and this user need a stream of entangled pairs for a given application, and also this user and this user need a stream of entangled pairs. So you can see that we need to perform some swapping operations here, and this user here needs to solve the scheduling problem, needs to understand which swapping operation needs to be performed first in order to maximize some metric of performance, which might be, for example, the rate of service of the two user pairs. Now, a thing that needs to be stressed here is that a core hardware difference between classical and quantum networks is how long information can be stored inside the memory. As I've mentioned before, even the best quantum memories can get to some milliseconds of storage time, and that's really pushing it. So you can see how the scheduling problem becomes extremely critical in quantum networks, because you need to figure out which operations to perform, and you need to do it quickly. So this is, as I've mentioned, a very well-known problem, also in the quantum side, but solutions are not as widespread. There have been some attempts to adapt the Max-Weight policies to quantum networks, and among which one by us, and it seems to be a feasible way. It seems to be a good way to follow, to try and adapt classical scheduling policies and see how they perform. And this is actually the context in which our work would be set, because our core contribution with this work would be to have designed a dynamical scheduling framework, a dynamically controlled framework that you can use to benchmark your scheduling policy over your quantum network and see how that policy performs, whether the network serves well its users, whether it doesn't, and if it doesn't, to figure out what you need to improve. So what we wanted to give the community with this work would be a tool for network design, because since the hardware is almost there and the protocol questions are starting to be posed, we feel that this is actually the best time to be starting to ask questions about protocol design and to be designing tools that people can use to implement networks. Yes?
I'm sorry, I will ask a very dumb question.
Yeah, no, don't worry, absolutely.
I didn't understand what is the specificity, because in a packet network you do a process before you transmit the packet.
Yes. Okay, so the specificity here to quantum networks is, let's just clean up this picture so that I can. Okay. Yeah, of course you do processes in classical packet networks. Yes. The idea here is that, first of all, as I mentioned, the process is not directional anymore, because you have something happening along the individual link and you have to stitch it together. So it's not something that goes from A to B, but it's something that grows from the middle of the network to the extremes. And then you also have specificities in exactly how the technology works, because it's not anymore a matter of having, for example, you have the distribution of pairs, and you need to get it to the users. But these pairs are probabilistically distributed, so you're not sure how many you will have. And that uncertainty is an uncertainty over how much resource you will have to serve your users. Because we had to deal with this problem actually when doing our work. The first analogy that we drawn when we were writing this work was that at a node, you can have some queues of classical packets, and you need to serve those queues of packets to achieve efficient service of the users. And we thought, okay, that translates really well to having queues of entangled pairs on the individual links, and we need to perform swaps to distribute pairs to the users. And actually, we noticed that this is an intrinsic difference in the problem, because those queues that we have are not queues of something that you need to remove from the network, because they're not requests. They are queues of resources. And you need to find a way to wrestle with these queues of resources and be able to serve users with a resource that you might or might not have. And it has a bit of specificities in that direction. And then you have all the idiosyncrasies of the hardware that works differently and all the elementary protocols that you have at the link level. Of course, this is a very, very abstract description, but the physics underneath makes it so that this is a different problem in some way. I mean, it's very similar to what you have to achieve in classical networks, but it has some specificities.
My other point is that 1
Yes?
millisecond looks a lot of time.
What?
1 millisecond sounds a lot of time for me.
It sounds like a lot of time, of course.
It's not enough.
So but that's my point. But
No.
This is behind that makes the issue
Yeah,
so low.
the physics behind is how you implement your memory. So to answer that, you need to go really, really deep in the physics of how you implement the memory, because but really quickly, a way that you can implement a quantum memory, let's say, is what we call the atomic frequency comb. So we prepare a crystal, a particular crystal, we prepare it with a frequency profile that's a comb. So something like this with an absorption profile that's, of course, it's not gonna be this definite. And what you are gonna do, you're gonna absorb a photon that has a frequency in one of those peaks. And then as the crystal evolves, naturally, the frequency there are some spins inside that that absorb this photonic information. It gets transmitted to a physical system inside that oscillates at a given frequency. And this frequency, of course, naturally goes down. So you're moving along this profile. And after you have moved up to about here, you re-emit your photon outside. And this is one idea of how you implement it, but it's not controllable. Another way that you can do it, you can exploit weird optical phenomena like electromagnetically induced transparency, which is transparency that you can induce in a cloud of atoms with particular radiation, so that you send your photon, you make the cloud transparent, the photon enters, and you remove the radiation so that the cloud is not transparent anymore, so the photon is trapped inside. Then you remake the cloud transparent and the photon can get out. But all these processes have enormously complex experimental apparatus behind them. So that, yeah, the main limiting factor here would be not the physics, but the experimental ability to implement these systems, because they are enormously complex. And yeah, here I'm presenting like a big network with plenty of memories on it because I'm a theoretician, but actually one of the setups that they have at in Jussieu, at LKB, is for one quantum memory where they send 2 photons inside and they retrieve 2 photons outside. And at the moment, that's about a room of equipment.
There is a theoretical limit, something that we know that we will not be able to do better.
Not that I'm aware. I cannot come up with it off the top of my head, so I wouldn't say so. I mean, in principle, I wouldn't say so. Maybe there is some limit that I'm not aware of, but I don't think so, because as long as you're able to better implement those processes, you should be able to push it up. So yeah, problem of scheduling, figuring out what swapping operations to perform in order to serve your users. Our contributions, as I said, introducing the model, which by the way can be used with arbitrary network topologies and allows for multiple commodities. So it allows for multiple user pairs that need to be served. And this, I'm not aware of other works that did this before. Then as a secondary contribution here, I've listed localized scheduling policy, in the sense that during when we develop this work, we show our tool, and then at the end we show some examples of how to exploit this tool to benchmark various policies. And one of the examples we proposed is this localized scheduling policy, which is an original policy that we propose to overcome some of the limits of the examples we provided. But it will become clearer as we go on. So now we can start discussing the work. We can get actually in the substantial part of the presentation. So the notation we use is extremely standard. We have an arbitrary graph with with quantum switches located at the nodes, and we say lossy fiber links across the edges of the graph. Of course, this is a bit abstract because actually in the links between the switches, you actually have a setup that can generate link level entanglement. So it's already a level of abstraction you have. And additionally, to make the statement of our framework a bit easier, we also exploit this extended edge set, which is none other than all the possible pairings of nodes that you have in your graph. So any possible couple of nodes that you could come up in your topology will have an edge in the extended edge set, even if it doesn't necessarily have one in the original one. In terms of assumptions, we make those two assumptions, which are not too restrictive. We just made them because we wanted to get the main point across. So the assumptions we make is that there are fixed user pairs, fixed Alice-Bob pairs, we call them. We know who those pairs are, so we know who's gonna request entanglement during the operation of the network. And then we assume that the routing has already been done, so that we do not concern ourselves with the problem of routing in this work. I should stress, as you see, that we do allow for the possibility of one user pair to be served by several routes, as you see there for the green one. And another additional assumption I should mention is that we will work in discrete time because it's simpler to develop the model this way. So yeah, before delving deeply into the parts of the framework, I want to give you a bird's eye view of what we are going to talk about. So for every edge in our extended edge set, so for every pair of users, let's say I and J, for example, our model will have an EBIT Q, which is an object. It's essentially a number. By EBIT Q, it's a shorthand for entangled qubits Q. It's essentially the number of entangled pairs that these two nodes share, because as the network operates, it will distribute entangled pairs to its users, and this EBIT Q will be the number of entangled pairs that we have between users I and J. Additionally, every pair in the extended edge set will also have what we call a demand queue, which is, again, the localized blob here. It's another number. In this object, we store the number of requests we have from the users. So suppose that, for example, this is one of our Alice-Bob pairs. I and J is one of our Alice-Bob pairs. At any given moment during the operation of the network, they will have a number of pairs that they have requested. So a number of requests that we need to serve. This is more similar to what you need to deal with in classical packet networks. And our objective here would be to develop a set of equations that describe how these two objects evolve.
Number of requests is number of qubits to be sent.
Yes, exactly. The number of entangled qubits that the user pair has requested, because you will have the pairs of users that want to realize any generic application, let's say, for example, QKD, so quantum key distribution, and they will tell your networks, let's say, I need a stream of entangled pairs at 500 kilohertz, let's say. Then another pair will tell you, yeah, but I also need a stream of pairs at, let's say, 200 kilohertz, and you need to keep all those stored and manage to operate your network in order to maximize some performance metric. So let's start describing the pieces of our framework. First of all, the EBIT-Q. This is the global expression that will describe the evolution of the EBIT-Q of a given edge ij. So at time step t+1, every Q will have, of course, the number of EBITs it had at the previous time step, plus aij, which is a random value that represents the amount of EBITs that have been generated during that time step. And I should stress that, of course, this A will be non-zero only for those edges that are actually connected by fiber. because it is the number of EBITs that are generated by the experimental system I have along a link. For example, if I have something like this, along this edge, which is not connected, the arrivals will always be 0 because there is nothing there generating EBITs. Minus the losses, because quantum memories are very prone to loss. So we have this exponential model, which is quite standard in quantum networks. This is what we call the storage and retrieval efficiency of the memory, which is the probability you have to actually be able to retrieve information from your memory. And it's again a random value that we extract according to this given distribution we have, and we use it to model the losses in the memories. Last term in the queues is actually the most interesting one, because it is the term that models the effect of swapping operations on our queue. So you need a term that, if you perform a swapping operation, let's build our system once again. Suppose I have one pair here and one pair here. I perform an operation and I will get one pair across this edge. I need some mathematical way to model this movement of pairs. By the way, I haven't mentioned, this is crucial, that of course, if I have an entangled pair across a link and I perform a measurement, which might very well be an entanglement swapping operation, I will lose the pair that I have across that link. So the measurement operation actually consumes the link-level pairs.
This is why we have a plus and minus?
Yes, exactly, because it might remove pairs from a queue, or it might give them. And we model this effect through this notation. We introduce this notation. So Rijk of t equals n. R for rate, because this term is the number of times that we perform a given entanglement swapping operation. And we have Ijk to represent that this is an entanglement swapping operation going from queues Ij and Jk to queue Ik, like this. Ijk, Jk. I have a pair here and a pair here. I perform the measurement at node J, which is in brackets, and I get one entangled pair across the two external nodes. So that this operation would remove one pair from queues Ij and Jk and add one pair to queue Ik. As you see below in the example, RABC equals 3 means that I remove 3 pairs from queues AB and BC, and I give 3 pairs to queue AC. So that once we introduce this notation, the complete evolution of our queue of EBITs would be Q plus A minus L, as mentioned before, minus the summation of all the rates of the transitions that take away pairs from my queue, plus the summation of all the rates of transitions that give pairs to my queue. And this is how my EBIT queue would evolve. Now this, of course, is the equation from one edge in the extended edge set. I need to phrase this equation for all edges in the extended edge set. So the most natural thing to do is to introduce a vector.
Just a question to go back. Is it on the edge of the network or any pair of...
Any pair. Any edge of the extended edge set. Yes, exactly. The full connected network, yes. With, of course, some differences in depending on what node what kind of link you're considering, because if it's an elementary link, you will have this term, while if it's not elementary, you will not have it. Okay, so yeah, we have the evolution of our queue. We move to a vector formalism. So moving to a vector form for Q, A, and L is straightforward. You just need to arrange all the values into a vector. For what concerns the scheduling side is a bit more delicate. So what we do is we introduce an R vector where we collect all the rates of all the possible transitions that our routing allows. And then we introduce we introduce this matrix. This matrix is strictly dependent on the topology and on the routing we have over the topology, because we collect in this matrix as many columns as we have possible transitions in our network, and as many rows as we have queues. And for every transition, we place a -1 if the transition takes a pair from the queue, and a +1 if the transition gives a pair to the queue. So that this matrix is effectively how we encode the topology of our network. Notice that since we focus on bipartite entanglement distribution, we have a net summation of every column to -1, because every operation will end up consuming one pair effectively. And you have below the full evolution of the queue. Now, the scheduler, if we plug it now in the network, the role of the scheduler will be to have some information about the state of the queues. It might very well know all the queues perfectly, and it needs to figure out what is the best R vector to serve the users. And it also needs to figure out which pairs can be released for the users to consume. So as you see here, those two things are actually missing. So let's start. Yes?
Say that the scheduler knows all queues, but so it means there is a way of exchanging information beyond the entanglement.
The scheduler may know all queues, because when you perform, when you implement any entanglement distribution protocol, you still need a layer of classical communication on top. So whenever you have your quantum network, you also have a classical layer on top of it to exchange control information for the protocols. And you might think of a scheduler that knows all the queues. I cited that as an example. You might think of that. And if you do implement that, you need, any-to-any communication in order to share how many pairs I have in each queue. You might, of course, work in other scenarios where you require less information for the scheduling decision. And so you would need less communication infrastructure. That's actually a key point that we will discuss during the example section. So yes, most definitely there is a layer of communication, because you need to exchange information to implement the protocols. But how specifically that layer of communication connects the nodes of the network depends on how much information you want to exploit for your decision.
What is the point of having this entanglement if you have another layer which is classical communication?
The point is that this entanglement-based communication enables applications that you could never realize in classical communications. For example, communication based on entanglement has security that's based on the laws of physics, because if I send you a message using these schemes and someone reads it, they will need to measure it. And the moment they measure it, they alter it, so that the information cannot be used anymore. Or, for example, another thing that you can achieve with this kind of quantum technology is blind computing. So, for example, let's suppose that I have a quantum computer and all the people in this room don't, and they want to carry out quantum computations. What you can do is perform computations on my computer without me knowing either what you're doing, nor what the result is. And this is something that you cannot implement in a classical communication. And also the textbook example of the difference between quantum computing and classical computing is that quantum computers can break all the encryption algorithms we have, so that there is great interest in pursuing this kind of applications, because they have completely different fields of application with respect to classical technology. So it's not like quantum communication is supposed to replace classical one. It's more that it's supposed to be on its side, to provide new ways to develop technology and new applications that cannot be realized in any way with classical networks.
So, but you still need to have something which is at this, which is a classical network,
Yes.
which will be the scheduler of these operations. And so, if I get it right, because this is what will, I mean, the communication there will.
To simplify, the classical network is used for the control plane of the quantum network.
Yes.
To get at all the signaling required for the things happening well in the quantum data plane.
Yeah, but assume you want to do a computation which you can only do with in terms of quantum computation. So won't it be slowed down by the control plane?
One of the problems we have in this comes back to the 1 millisecond question is when you're transmitting qubits, there are on the classical network round time trips that are happening for the signaling, and you're dependent on those. And a lot of some work that's going on is trying to get as little round time trips as you can, because with those round time trips, the current buffer lifetime is too slow to actually. It's part of the problem that we're looking at.
Yes, exactly. And you have also a problem that the information that you store inside the memory will naturally degrade because it will decohere, there are a lot of physical processes going on that will degrade your information. So you need the communication that's as fast as possible. So yeah, as I said, we have those two last points that are missing. We need to give pairs to the users so that they can use it, and we need a way to account for user demand. So first of all, how do we allow our users to consume our pairs? We do so by extending a bit the reach of our problem so that our matrix will not anymore only have the topology and the routing of the network. We also add a -1 for each individual queue that we have. So it's a negative identity block essentially. And then we add some R terms that are relative to single queues, so that the scheduler, which again, whose purpose is to find out what the best vector here is, will be able to set, for example, let's say RBC equal 2, and that will mean, when I multiply by this matrix, a net -2 over QBC. So essentially, this is modeling the users measuring the pairs for their application and consuming them and removing them from the resource pool of the network. The final step we need to take here is to put inside the framework some way to account for user requests, because as of now, the scheduler has no way to know what the users want. So to do so, as I mentioned in the bird's eye view, we introduce a second object, which is the demand queue D. So D is essentially the number of requests that you have across a given user pair. And it evolves as dt+1 equal the requests you had at the previous time step, plus the new requests you've received by the user, which inside our simulations we model as a random process, plus, which here will actually be minus because it's this vector minus the M matrix. I'll show you why. The service term. This term models how you serve the request, because look below there. The N matrix is defined as the N matrix we had before, so topology minus identity, but we zero out all the topology related part, so that if this R vector features some swapping operation, it doesn't affect the demands, but if it features some consumption operation, it will be multiplied by the negative identity block and will remove one qubit from the related queue and one demand from the related queue. So actually what this is doing is modeling the service of demand by the network. Yes?
Are there some constraints also that you cannot serve more that you have?
You of the model, we will have constraints when we actually develop the scheduling policies, and they are actually one of the main points that you need to debate over, because you can enforce strict constraints, but that makes for a slower scheduler because it has to consider more constraints. or you can enforce less strict constraints and have a scheduler that maybe will ask you to perform 4 swapping operations, but you have only 2 pairs. And in that case, you are not able to serve it. So it's actually a trade-off. You have to, it's actually where this work becomes useful, because you can phrase different scheduling policies with different constraints and see how they fare in the network. So to recap, we have for each pair of nodes in our fully connected network, we have an EBIT queue and a demand queue storing the resource and the demand we need to serve. The operational scheduling amounts to deciding the R vector given some degree of information about the network. That's intentionally vague because different scheduling policies will require different levels of information. And the information we have about the topology and the routing of the network is inside the M matrix that we described. So now let's look at how we applied this framework in benchmarking some policies. What we did was examine different kinds of scheduling policies in order to analyze, first of all, how they perform, and second, if it's actually useful to try and adapt them to quantum networks and to have a tool that benchmarks them. So the first policy we tried to benchmark was the greedy scheduler, which is a concept we borrowed from classical networks. So by greedy scheduler, we mean a scheduler that whenever there is possibility to perform a swapping operation between contiguous queues, it will do it, regardless of the demand of users, regardless of any other factor. Whenever there is resource, the greedy scheduler will consume it. The only thing that it regards is the routing of the network, in the sense that it will, in such a situation, it will not perform swapping operations that would pull back to lower levels our entangled pairs. It will always strive to serve the routes that we have. So here we can tie in the point about information that we had before, because this scheduler does not need communication infrastructure other than the one that you need to implement the quantum protocols. You do not need, for example, to communicate the status of a queue that's here to a node that's here in your network. So this policy is the best, arguably, in terms of communication efficiency. But as you can imagine, the performance is pretty poor. So to provide kind of an upper bound of scheduling performance, we borrowed, again, a concept from classical networks, and we implemented a max weight policy on quantum networks, which we call the full information max weight policy. So what this policy does, without delving deeply in all the calculations, what this policy does is it knows everything about the phenomena in the network. So it knows all the queues, all the demands, all the arrivals. It knows everything that's going on in the network. And it uses that information to phrase an optimization problem and solve it for R in a way that minimizes the accumulation of both demands and entangled pairs. What we obtain is that this policy is optimal in the max weight class in terms of performance. But of course, we have extremely large communication requirements. And actually, we have large communication requirements to the point that this policy is almost never actually usable in real networks. Because, of course, if you need to communicate to a remote node the state of a queue that's physically far, the information will need to travel from this queue to the node. And in the time it takes for the information to go to the node and maybe to come back, depending on how you implement your communication scheme, the system will continue stochastically evolving. So it will continue generating pairs, it will continue losing pairs, so that when the information gets to the node, or rather to the central scheduling authority that will carry out the scheduling decision, the information is outdated and the decision is not applicable anymore to the state of your network. So this is the main shortcoming of this policy, that However, when implemented in simulation, shows very good performance. I will show you some plots later. Finally, the last example of scheduling policy, which is the one I kind of teased in the introduction, is the localized information scheduler. Looking at the problems that I described in the full information scheduler, we thought of a policy that again solves an optimization problem, but it does so in a localized way. In this policy, every node solves its own optimization problem without talking to a central scheduler. And the trick here is that this node will use exact information about the queues connected to it, because it knows it, and averages for all the other queues. So average arrivals, average losses, and it will build an expectation value and plug that into the optimization problem in order to obtain a local scheduling decision. Every node does this, so that every node obtains the swapping operations that it needs to perform. What we were hoping to achieve with this policy was to have something that gets close to the fully informed performance while not having the communication problems that I described. So now I will show you the 3 plots related to the schedulers. So this is the one related to the gray scheduler. In the paper, we wanted to propose a simple example. So what we did was examine this chain you see at the bottom, where the user pairs are A, B, and B, F. And we wanted to focalize on the link level congestion that we will observe here. So what you see here is the percentage of unserved user requests at the end of a simulation run. And on the axis, you have the demand rate, average demand rate across the first pair, and the average demand rate across the second pair. While this diagonal here is the physical limit for service of requests. What we observe with the greedy scheduler is that we are not covering a big portion of this region that we could physically achieve. And also an interesting thing to notice is the shape of this region. This region is a square. It is a square because suppose that you are, for example, in this point, and you increase demand across this axis. In principle, if the scheduling policy were aware of demand, you would expect that you would try to serve more the pair that has more demand. You do not observe this because the greedy scheduler does not regard user requests. So what we see is a square, and it's not very good performance. When we actually move to the fully informed max weight scheduler, we observe a great increase of that performance region. And we observe also a different shape. We observe a different shape because here we actually observe the 2 pairs competing and the scheduler trying to manage this competition, while here and here it can ensure full service without having to manage competition between the pairs. So what we observe is first that it's a good idea to try and adapt classical scheduling policies to quantum networks, and second that it's useful to have a tool that allows us to quantify this improvement. And finally, we will look at the results for the localized information scheduler, which, as you see, were very, very promising because they are almost on the same level of the fully informed one. Of course, we cannot expect to get the fully informed results, but we can get pretty close with a policy that in principle should be actually implementable on quantum networks. So to conclude, yes?
You still see the squares in the border, right?
What?
You see the squares in the border.
Here.
There and then, yeah.
Yes.
My question is, if you added to this information the one hop information, the information about the neighbors.
Yes.
You would be able to.
Yes, it would. Yes.
You did a little bit the squares.
I think you already have it with the full information case. Can you go back to the full information? You already have it.
Yeah, no, but there are actually some things that create this shape. So, first of all, losses. because if we try a perfectly lossless scenario with perfect information and everything, we are able to cover the first triangle. We introduce losses, we lose a bit here and a bit here. Then what you can do is you can, so what we did here was the first work we did, and we focused on optimization of both the demand queue and the EBIT queue, because we wanted to ensure uniform usage of resources. What we actually observe is that if we only focus on user requests, we will get a bigger region, which is only limited by loss. What you say, however, is very, very interesting, because what you actually can do is that in a scenario in which the full inform is here, if you add one op from here, you get here. You have two ops, you get here. And if you go on, you get to the limit where you have information about the full network, and you recover the full information scenario. So that is definitely a good idea, and it's something we are investigating in further work, because we are working on the actually extended version of this work, because this was a conference paper, so we have to make it respect a certain limit on length, but we are working on the full version. So to summarize, we introduced this framework, which is dynamically controlled. It worked on any topology, and it allows for multiple commodities. We demonstrated that it could be useful as a benchmarking tool for people to use in their network design work. And then we introduced this policy that it's shown to be very promising. Now, of course, we need, as you see there, to first of all and foremost introduce quantum noise. And when you present this work to a quantum audience and you say we need to introduce quantum noise, everyone goes, because it's the most important thing to do for this work. It's something we are doing, we have on our radar, and it is paramount to achieve. Because other than losses, you also have all those factors that we're describing before, like the information degrading with time, like the memories also not being perfect, and you can account for those in a more refined way. However, we introduce just losses because losses are by far the leading cause of imperfection of quantum systems. So even with this elementary level of imperfection accounted in the model, it's still a relevant result. Then, of course, we would like to benchmark more complex topologies on more complex policies, which is what we are doing right now and will have in the extended version. And finally, for long-term future work, it could be useful to integrate this scheduling model with a routing design tool in order to have a complete quantum network design toolchain. And with that, I will thank you very much for your attention. And if there are any questions, I'm very happy to answer.
Thank you very much. Any questions in the room?
I have a question.
Yes.
Is there anything new from this quantum network from the traditional network? I mean, maybe in the traditional network, these three policies have the same inner behavior, right?
Yes. What do you mean? Anything new in terms of problems or in terms of applications?
In terms of the protocols, in terms of which policy should we choose?
Well, which policy should we choose? I think it's way too early to ask that question. It's as of now, we are starting to see the first networks. So yeah, we are developing the tools because we would like to answer that question. We would like to look at a network and know how to control it when the hardware will be there. So as of now, I couldn't tell you what the best policy is, simply because there are not that many scheduling policies on quantum networks. It's a pretty new field. So we are starting work on that in order to have the tools and be able in 5, 10, 15 years to answer that question over a working network.
It's interesting to note that even though the tools like Maxwell feel old, the queues we're applying them to are really not the same ones we're used to.
Yeah.
So it's old tools applied to a very new, different setting.
Exactly. Exactly, because as I mentioned before, in the normal phrasing like the Maxwell, you have queues for messages, while here you have queues both for demands, which mirror the messages because they are requests from the users, and for the resource you are using to serve those demands. So it's actually, it adds a layer of complexity to the initial problem that you had, because you have the queues you are, let's say, used to because they're similar, but you also have another problem in managing variable resources.
And namely, you have queues for every pair of nodes.
Yes.
Even if they're not linked.
Yes.
And even in your policies, when you have local policies, you're managing a queue with every other node in the network.
Yes.
Not just the ones around you.
Yes, exactly.
Which is it's one of the downsides of the model, right?
Yes.
It's something you'd like to get rid of.
Yeah, the scaling in terms of the number of queues is not great, I have to say. But as of now, is something you have to deal with. And actually, it's something that gets even worse because let's go back here. So as I mentioned before, here, we are focusing on bipartite entanglement situations, but entanglement can be shared between 3 or 4 nodes or however many nodes you want. And if you wanted to care for these cases, it means that for every possible kind of entanglement, you have to include a queue. And so the scaling of this thing becomes worse and worse. So
the protocols would be different, right? You would generate those, not pairs, but groups somewhere, and then you would swap each qubit.
Yes, but yes, of course. But at the end of the day, you still have some queues that you need to manage and to deal with. So yeah, that could be one of the biggest shortcomings here. But it's something that we are working on because we are looking. Let's say, for example, you have a topology like this. The question we're asking is whether you need individual queues for these links here, or you can just abstract them away and just think of an effective queue here. So it's interesting to have all these questions because this is not a field that's as well established as classical networks. So all these questions find useful work. All these questions are something that you could actually pursue and do useful work on. That's the most exciting thing about this field, I would say. Yes?
I'm sorry, I didn't understand everything, of course.
Don't worry.
But I understood that you are doing some estimation of what's going on in the other nodes,
yes.
Right? By averaging
yes.
information. We're using the same time scale for averaging in all the nodes. Because you could imagine that you're clustering your nodes, and for those that are in a given cluster, I mean, at the first level, you have something hierarchical, right? Cluster, inside the cluster, you use a time scale, which is a short one, and then you go up with a longer time scales, reduce the time and the amount of information you need to exchange. So altogether, maybe you can enhance the performance. Right?
Yes, that would be a very interesting way to also to generalize our policy, because in this work, we just assumed that we knew the averages of the processes and they were constant, but of course, if you want to do it on an actual network, you need to work with rolling averages. And so, yeah, doing it like that would allow you to explore more refined and more complex scaling policies while still retaining that advantage of not having to communicate everything. Because if you're building an average, you do not care if the information about time step 7 arrives at time step 13. You don't have that kind of pressing hurry that you have with having to decide over the actual state of the queue. So yeah, that would be most interesting to investigate.
So time for one last question, if any.
I have two.
You can ask me later.
Close with that. Okay.
The first one was, did you try any stochastic schedulers?
No.
Okay. And you haven't implemented it in continuous time?
No.
Things like that.
No, those are all discrete times implemented through a Python simulator with discrete time schedulers, all solving that optimization problem at every time step. So no, nothing stochastic.
So thanks again.
Thank you.